Okay, let's start the second part. We are happy to have Timo Vilkas from Göteborg, and he will tell us about long-term behavior in opinion dynamics, clustering versus consensus, and local versus global. Timo, please, screen is yours.
Thanks, Nina. And also thanks to Nina and Julian for inviting me to speak here. Not often these days you get a chance to speak in front of public, at least in this kind of setting. The title might sound a bit bigger than it is, so I'm not going to talk about long-term behavior in all kinds of opinion dynamics, but instead I will show you some models so you get a flavor of what different kind of long-term behavior there is to be expected or seen. So let me give you a short outline of the talk. So first, in good tradition, as Elhanan did, I want to start with the voter model, just because it's simple and anyway interesting. And then I want to give you an idea of what you could look for in terms of long-term behavior and what possible limiting behavior we have in other models, not necessarily the voter model. And then I will walk you through as much as I know about the bounded confidence model that was introduced by Buffon, No, Amblara, and Weisbuch in 2000. It's maybe not as known as the voter model, but interesting enough to be featured here. And at the end, I want to talk about what we called the compass model. It's a variant of the model by Buffon and others, where it's even more so obvious that there is a dichotomy between local and global consensus. This is all based on work together with Ulle Häggström here in Gothenburg and part 4 with Nina and Markus in Munich. So as before, we are going to look at the network graph. For our reasons or purposes, it's enough to have simple graphs with vertices and edges, and we see the vertices as agents and the edges as connection between two agents where they have the chance to meet and discuss or influence each other. And at every vertex, we will have an opinion. I write eta t of v for that, not x, but that's the same as Elhanan did. And as I said, the edges give rise to influence of agents to each other. So they can lead to updates of opinions, either in the way of the voter model that one takes the opinion of the other, or as in those other models, you will see more like a compromise style of behavior. And obviously, those local interaction rules give rise to some macroscopic properties of the model, and especially the long-term behavior. And that's what my talk is going to focus most on. For my purposes, I'm going to restrict the opinions to some opinion space. Can be 0, 1 as, or -1 + 1 as in the voter model, but later for the continuous models, it will be an interval or even all of R or even higher dimensional, but that's not the direction I want to go most into. But just think of there is a space of opinions and we have initial opinion values at every vertex, and they are taken to be IID, so same distribution and independently of each other. And we focus on pairwise interactions. That in some sense is a restriction because there are a lot of interesting models where, as the one that Elhanan just showed, where information is coming from a group of people to me, like for example, all neighbors, or everybody at graph distance at most 2 or something like this. And then my next opinion is based on that. Instead, in the models I'm looking at here, it will be pairwise interactions. So 2 people meet, discuss, and then depart with either the same or a different opinion. So as a warm-up voter model, second time, and now I'm not sure that this introduction is a better one. I also want to spend some minutes talking about it. Okay, it's not -1 + 1, the opinion space now, but instead 0, 1, 1 for me, or blue, red if you want to stick to the name voter model in a more literal sense. And we take the opinions in the beginning to be uniform, so a half for 0, a half for 1. And as Elhanan already explained, we have like Poisson clocks ticking on the edges, and they have, say, rate 2, and every time the clock goes off, those neighbors meet, and then you flip a coin who takes the opinion of the other. So if they have the same, no change. If they do not have the same, then either one neighbor imposes the 0 on the other neighbor who had a 1, or vice versa. And especially, so I want to more focus on infinite graphs here, especially if you have a graph like ZD, for example, you would have a conversion rate from your current opinion to the opposite at the number of neighbors that have this other opinion. So that's not hard to see, and I guess that's enough for understanding the model. So if we look on Z, that's very simple. You have two neighbors. All of them are either, all of the nodes are either 0 or 1s, blue or red. And if you consider the edges that go in between, I just have to move a bit around here. If you consider the edges that go in between two colors, you will easily understand that those, call them separators or inter-cluster edges, they perform simple symmetric random walks, because depending on which of the not agreeing neighbors takes the opinion of the other, this inter-cluster edge will jump to the left or to the right. And those simple symmetric random walks are annihilating. So as soon as two of those edges or separators collide, they will disappear, because that's when the neighbor, or like, think about this blue vertex here. If he takes the opinion, or she, of a red neighbor, then these two will just coalesce and disappear. And by that, you soon start to realize, okay, if the time just goes on and on, what happens is that all my neighbors and their neighbors and so on will have the same color. So we have some local smoothing of the profile, if you wish. But however, at any time, there will be huge patches of blue and huge patches of red, and not one color takes over, and there will be some kind of a global consensus. So here you already get this flavor of, locally I see only one color, but the whole graph does not reflect this, consensus. And obviously, if you go in higher dimensions, this, what I tried to sketch here, this kind of proof that locally they would agree, and there's just a few interfaces that wander around and all of, like, after a while coalesce and disappear. In ZD, it's a bit more difficult to think like that, but you can do something similar, namely you backtrack your opinion. So if you're a vertex and you're 0 or 1 right now, you can start looking back in time. Where did I get this opinion from? Aha, the neighbor from the right, maybe, if that makes sense in ZD. And well, this neighbor maybe had this opinion not from the start, instead also got it from some other agent. So you backtrack all the way back to t equals 0, and you will end up at some vertex where this opinion originated. So this one person forced it on some neighbor, forced it on some other neighbor, forced it on the next neighbor. Could even be loops there that it comes back to the same one, but whatever, you know what your opinion is, where your opinion is coming from. And if everybody does that, you see that it's a symmetric random walk once again, and those are coalescing ones. So as soon as we have the same, how to say, origin of an opinion, a current opinion, then the further history back in time will be the same for both of us. So that means as soon as, say, Nina's and my coalescing random walk back in time meet, we know that in the time now, we have the same opinion because it came from the same origin. So you can guess how the theorem goes, and here it's written down. It's Holly and Leggett who proved that in 75, that obviously, just as simple symmetric random walks are recurrent in 1 and 2 dimensions and not recurrent in 3 and higher dimensions, same happens here. So the limit that of the probability that two people agree, and here it's not even necessarily neighbors, is 0 for d equals 1 and disagree, sorry, is 0 for d equals 1 and d equals 2. And for even higher dimensions, there is a positive probability that we would not agree even if we're neighbors. So that's what I wanted to say about the Voto model. And as a change to that, I want to introduce a more continuous model where we don't have opinions 0 and 1. Instead, we have opinions in the full spectrum in the interval from 0 to 1. And on top, we get a confidence bound, theta, which is meant to give some kind of a notion of tolerance. I'll come back to that. And what they call the willingness to compromise, mu, that gives sort of the step size towards a compromise. So how do I mean? Well, we still have a graph. We still have a Poisson blocks on every edge. So why those Poisson clocks? I mean, if you're in a finite setting, obviously the next clock that goes off is just uniformly at random. So it will be just picking a random edge. If you have an infinite graph, it's a bit harder to pick a uniformly at random edge. So you have those Poisson processes, and whenever there is an event, these two people meet and discuss. And those drive the dynamics in updates here that look like I wrote down. So if the opinion just before time t, when the Poisson clock at the edge uv goes off, were eta t minus u and eta t minus v, those two people will meet, exchange their opinions, and then update their opinion of the form that Elhanan already sketched, that maybe the first person is a 0.8, the other person is a 0.4, and then they approach the common average by going a step towards the other. And the step size is this mu. And where does the confidence bound come in? Yes, they do so, but only if their opinions were not too alien to each other. So if I'm a 0.8 and say Julien is a 0.4, and the common confidence bound, it's the same for every agent, is 0.3, we would just consider the other person nuts and not change our opinions whatsoever. So this is I don't know, a little bit more realistic version maybe of the Voto model, because we do not just take another person's opinion, but rather influence each other in a mutual situation. And plus you have here the option to say, no, this person is nuts, I don't listen to him or her. And you could think of the spectrum 0-1, as Elhanan said, maybe left and right wing, your positioning in the political spectrum. But also you could say 0 is the, or like 0-1 is the spectrum, what you think is the best strategy to fight COVID. So 0 would be a social liberal Sweden before they found out that restricting the access to elderly homes would be a smart thing to do. And 1 could be what Santiago de Chile, for example, did when the first wave of infection was going, where you had to apply online for a time, I think time slots of 1 hour, in which you actually are allowed to leave your apartment, no matter if you need food or the doctor. So there you would meet a person who says, no, I think what Sweden does is perfect. And another person thinks the more restriction, the better. They would just consider each other as stupid as can be and not change any of their beliefs. So, and what can we say about this model? Wait, that was a jump. Well, it has limiting behavior, just as the Voto model. And we want to distinguish 3 of them. You might feel that there's something missing, but I get back to that. So the first setting, the first limiting behavior would be disagreement or clustering, that there will be finally incompatible neighbors. So there might be neighbors as to vertices sharing an edge that end up in the situation where they consider each other nuts from a certain random time, big T on, forever, and they will never ever again update their opinions, although they have the chance to meet and influence each other, just because they're too alien. The second one, which I call local or weak consensus, would be that 2 neighbors will finally concur. That means the difference of their opinions goes to 0. And the third one, strong or global consensus, that everybody converges to the same value. So now you might take a minute and think, okay, local, global. If we're talking a finite graph, obviously, first of all, you will realize that the strong consensus implies the weak consensus. So it's the wording is okay. But in a finite graph, you would even have that they're equivalent. So if weak consensus happens on a finite graph, it necessarily means that all the values actually converge to a common limit. But on infinite graphs, there is actually no such implication from weak to strong. So there we can actually distinguish all 3 of them. Now, thinking of this bounded confidence model, you might get the impression, but what if maybe the neighbors are incompatible, then they are compatible again, then incompatible, then compatible again? Why can't it jump back and forth like infinitely often? There's a kind of neat and simple energy argument that it cannot. So every time they compromise, some energy is lost. And if they sort of jump back and forth between big difference between opinions and small difference of opinions, the energy that is lost is infinite in the mean, and that's a contradiction. So actually those 3, you can show that for P almost every omega, one of those three will happen, or rather to say one or two will happen. So either two neighbors disagree once and for all, or they will approach the difference 0. But think still about that this can happen in bigger and bigger waves that are smoothing out so that nobody is converging, yet locally they are agreeing, but they're moving in sort of big waves. So that's sort of what is the tricky part in between those two. So this situation I would consider as agree to disagree. The first one. So the first result in this model for infinite graphs was done independently by Lanchier and Hegström in 2011. Their methods were not quite the same, but the strategy of proof was similar at least. So I don't know, you can maybe, if you're interested, check both papers and decide which one is the better reference here. I'm slightly biased here. And they showed that there is a phase transition if you start with the uniform 0, 1 opinions. So everybody gets a uniform number between 0 and 1, how much restriction they think is most reasonable. And we fix mu. It will anyway not play a crucial role, interestingly enough. And the phase transition in the confidence bound theta then lies at the critical value 1/2 in the following sense. If theta is bigger than 1/2, the limiting behaviors almost show strong consensus. And I haven't said that, but I should have. Let me go back. So here you see two limits, here and there. And there is actually nothing said about what kind of stochastic limit we have. In probability, in mean, almost sure. But this energy argument that I sketched actually shows that for the deform model, we can focus on almost sure behavior. In the compass model, I will get back to that. But for now, just consider those limits to be almost sure ones. And even more so, what you might have already started to wonder, I guess, nobody wrote in the chat, but since all those three events are translation invariant on a transitive graph, all of them are almost sure or 0 events. So this happens either with probability 0 or 1. All three of them. And this phase transition now says that if the confidence bound is big, so people are tolerant, in the limit they will all agree on one value, and this has to necessarily be the mean, because as you might have figured out without me saying that, this update rule is not only symmetric, and by that there is no favor given to one of the two people meeting, but it also preserves the mean. So the average value of the two opinions stays the same, although they update. So the spatial average is 1/2 from the beginning, and that won't change. So if there is a common limit, it has to be the mean. And for theta small, in that sense, smaller than the critical value 1/2, there will be those incompatible neighbors. So we'll have almost true disagreement. Now, I don't know, I guess most of you have heard this quote that the math talk should contain both a proof and a joke, and preferably they shouldn't be the same. I will give you sketches of proofs and maybe sketches of jokes. I hope you're happy with that. So how is the strategy here with those two settings? The idea to look at points that are a bit special in the configuration. Let's say we look at the origin, and we will call the origin epsilon flat if it has a certain property, epsilon flat to the right, let's say, if itself. So I try to sort of picture here the opinion of this. On the left, you see 0 to 1. So that's my opinion spectrum. So this one is really close to the mean 1/2. The next one might be given a little bit more margin, but they're all close to 1/2. And then the margin gets bigger and bigger. And how do I mean that? I mean, I want to choose the values of them such that any average to the right. So if I take the opinion values of the first three guys and average it, it will be not further than epsilon from the mean. And that for 3 to the right or 17 to the right, or as many as you want to the right, then we will call the origin epsilon flat to the right. So why is this interesting? This is interesting because just the same way as in the voter model, we were backtracking the opinion where it comes from. So we can do the same here. However, it will not be this random walk. Instead, it will be a weighted average of initial opinions. So depending on who interacted, my current opinion is a convex combination of all kinds of people opinion in the beginning. And on set, you can actually show that the contribution of somebody cannot be more than 1 divided by the graph distance plus 1. So people further away will not have the option to completely turn around my opinion. That's in strict contrast to the voter model, where everybody, no matter how far away, can completely change my opinion. And this leads to the fact that those epsilon flat vertices, they will not have the chance to get far away from the mean, because their opinion at a later time point will be just an average of opinions near, and the weight goes down with distance. So if the margin becomes only slightly bigger as distance grows, and there are only 2 vertices at a given distance, then all their future opinions are sort of stuck near the mean. And that leads to the fact if say the origin is epsilon flat to the right and -1 is an extreme person having an opinion near 1, say, they will be incompatible no matter how the future interactions are happening. So that would prove the subcritical case. And on the other hand, if you have a vertex that is epsilon flat in both directions, then you can show that this person 0 in my case cannot get further than 6 epsilon away from the mean. And by choosing epsilon small such that it fits in between 1 minus 2 epsilon minus 2 theta and 0, this person will be compatible to its neighbors no matter what. And this leads to the fact that also the ones left and right of it by this energy argument have to converge to the mean. And this, I guess you can see the point, inductively leads to everybody converging to the mean. So that was the sketch. Let me give some comments. What is a bit maybe disappointing or surprising, that it doesn't take into account any of the dynamics. So already at the beginning, you look at your configuration and you can say this person must be stuck close to the mean. That's at least the idea of proof here. So we don't use any of the dynamics. We basically use the worst case scenario for changes in one opinion. So that's a bit crude. Plus the result doesn't depend on mu. Mu is somehow just governing the speed of things. And even more disappointing, the critical case is wide open. There's 2 to the what Elhanan said, there is nothing known about the critical case as far to my knowledge at least. So why do I give you this sketch if I'm not even involved in the proof of this theorem? Basically because it shows the difficulties and the strategies you can have to handle those kind of models. So maybe let me give you this one next. You can do that not only for uniform 0, 1. Nobody's writing in the chat, but this question I assume would have come if I waited a little. Can you do for something else than uniform? Yes, you can. There's one thing you have to be aware though. So this a half, where does it come from? It's basically the distance of the mean to the extreme ends of the support of your initial distribution. So the a half is basically the distance from a half, which is the mean, to the ends of the spectrum 0 and 1. But for general ones where you don't necessarily have all the opinions in between, it can be that there are gaps in the distribution, then you have to also take into account those, because obviously people from this end of the opinion spectrum and this end can never talk to each other or compromise if the tolerance doesn't bridge this gap. So there you get a maximum between the largest gap and the distance of the mean and the ends of the spectrum. Also observe that in this case, when you have that the expected value is not lying in the support of nu, this idea of that I sketched here, that there is a positive probability that the vertex is epsilon flat right from the start, which sort of forced a positive or required a positive probability that you can be near the mean in the beginning, that's not given here. So if you want to prove the same for more general distributions, you have to be a bit, you have to work a bit extra to show at a later time I can have vertices that are near the mean, and by that epsilon flat vertices. But in general, the structure of the proof is pretty similar. Now, the next question you can ask, if we can do it on Z, how about higher dimensions? Yes, if D is higher than 1, or like bigger than 1, you can say something, but surprisingly little. At least we can say surprisingly little. What we can say is if the tolerance parameter theta is big enough in terms of the uniform 0, 1 from the beginning 3/4, there's at least weak consensus. So neighbors converge, or the difference of neighbors converges to 0. The strategy of proof is pretty simple. I just sketch it again. The thing is, if they would not, so if they had disagreement, so if you had the clustering into different groups, that can only happen if people end up with opinion values bigger than, what is that, 1/8 or smaller, no, bigger than 7/8 or smaller than 1/8 if the tolerance is 3/4. And that would force the final configuration to have a higher energy than the first, so the uniform 0, 1. And that's contradicting the energy argument. So in that sense, they have to somehow, they cannot disagree, because if they could, they would get stuck in a too high energy configuration. Again, you can do that for more general initial distributions, as long as you don't have the worst case where both are sitting at the end of the spectrum. So the next idea we had, because there is no result for the small theta case, so there is nothing said about if theta is small enough, then we have disagreement. That was surprising and disappointing. So we started to look at the same model on, instead of the whole grid ZD, only on the bond percolation. So you do a supercritical bond percolation on ZD, you will end up with a random graph, and then you perform your model on this realization of the bond percolation. The percolation should be independent of everything else, so both the model and the Poisson processes and everything. And we got the following result, which might be the first and only result you've seen where you can say something for non-trivial percolation, but not for the trivial case where P is 1. So in case P is supercritical, but not 1, so we have edges missing, but a giant component, like an infinite component, there cannot be strong consensus for theta being smaller than this radius of the support. So if you're stuck with the uniform 0, 1, it would be a half. Before I give you the sketch of the proof here too, as I said, it's a bit surprising that we cannot lift this argument to the full grid. And what you also might realize fast is that here it says we cannot have strong consensus for small theta. So that leaves us with two cases. Either it's weak consensus all the way, or we have a phase transition at some point between either disagreement to weak or weak to strong, or even all three. So that's open, but at least something. How the proof goes, this picture, you know the saying that a picture says more than 1,000 words. So I save on the words and give you the picture. We will just think about two copies of our IAD percolation, bond percolation. And in copy 1, the edge between U and V is not present. In copy 2, all the edges are the same, but just this one edge is there. So they have a positive density on each other. If this configuration can happen, then the other one can also happen with positive probability. And how do we think now? Well, we assume the opposite. We assume that there was strong consensus on the infinite cluster. That would mean that V in copy 1 converges to a half, because the argument is still the same. You have infinitely many vertices, so their average is a half. So if they even out in the strong sense, the average is a half. So V will approach a half. And if we just wait long enough, V will be very close to a half. And if theta is smaller than a half, then we will have an extreme opinion here at U will have a distance to the opinion that V already approached that is larger than our confidence bound. So in this, it's not a problem, because here in this, U in this first copy, U and V are not in the same component, so they will never interact. But if you think about it, that U doesn't have any other neighbors, and it's connected to only V in the second copy, now that makes it in the second copy a part of the infinite component. And if there is no update on E, even that can happen with positive probability until this time big T, where V for all the future will sit near the mean. Then those two, even though there is an edge present, will never start influencing each other, because this one has an extreme opinion. This one already converged so close to the mean that it will not keep talking to you anymore. So in short, if there is a strong consensus on the infinite cluster, if you assume that, then you would have that there's also a positive probability that there's disagreement on the infinite cluster. Because if this one is converged close to a half and this one has an extreme opinion, it will prevent them from talking to each other. And by that, and U has no other neighbors, U is stuck at the initial opinion for the rest of the process. And since they were all almost sure events, that cannot happen. So you cannot have strong consensus with positive probability and at the same time a disagreement with positive probability, as also in the bond percolation setting, we're still translation invariant. So all those three scenarios are almost sure. And here it sort of felt that in all this set B setting that the weak consensus is more like an annoying intermediate thing that you cannot rule out, or it requires at least some brilliant idea or better technique to rule it out. But it never felt like a natural thing to look at. It, like you never had an appreciation, or I should talk about myself. I never had a real appreciation for it until I was invited to come to Munich, and Marcus and Nina sort of motivated me to look back at things, and we started to try to figure out what this what really is going on with this weak consensus. So we came up with another model. It's in some sense a generalization of this default model that I just tried to analyze as much as I can. For the default model, by the way, there are results on with higher dimensional opinion spaces. So this is not the generalization that S has now 2 dimensions in my picture. But always, since the updates are sort of along the line segment between the 2 opinions, always you assume the opinion space to be convex. Instead, if you replace this line segment between 2 opinions along which the compromise takes place by a geodesic, so like here in the picture, you have an opinion alpha and an opinion beta. In the original model, you might not be happy because you could create opinions that are not in the opinion space by compromising. Instead, you take the geodesic, then this problem is solved, and it's sufficient to just ask S to be path connected. So the same update rule as before, just now you walk along the geodesic towards each other instead of the line segment. So observe that this makes it qualitatively different because you do not necessarily have that the mean of 2 opinions is preserved. We even more so made our life easier by looking not at some fancy opinion space. Instead, we took the unit circle. So think of the angles on the unit circle to be represented by 0 to pi or minus pi pi, and then you kill the pi just to not write so many pi's. So -1 to 1, say, where -1 and 1 correspond to the same angle. And if you have an opinion alpha, then that would be an angle towards either 0 or this point where you glue the ends together, doesn't matter really. And if 2 people meet, and for this model, we completely dropped the bounded confidence. I mean, you can start asking and thinking about it, but for what I'm going to talk, it's enough to just drop it and say theta is 2, so that everybody can talk to everybody. So if those 2 people are discussing, it might be pitch black there in the desert, and they're discussing where is the closest water source. They might not have the same angle in mind, and then, but still understand the arguments of the other, why it should be in this direction. So they might approach to some compromise. So they adapt their angle guesses towards each other. And you might think, okay, what happens if they're diametrically opposed? Well, then we have 2 geodesics, so we just flip a coin if you wish. But since we are later going to start with uniform initial opinions, this will anyway not happen with positive probability that you end up having two neighbors sitting on exact opposite points of the circle. When it comes to the distance between two opinions, we have to be a bit careful now. It's in principle the absolute value between the two angles. But since it could flip around, let's say, if the distance on the other side of the circle is shorter, then you would have to take this one. So just as I said, you have in principle two options for geodesic. So it will look like this, but in principle, it's the average, the absolute value distance just on the right side of the circle. But we have to do something because just taking the absolute value as of the difference will not work because it's not the shortest difference between them. Yes, and the theorem we got is the following one. The limiting behavior of the compass model on the like two-sided infinite path said, if you start with the uniform opinions on the unit circle, actually shows this weak consensus and in a strict sense. So we can show that there is no strong consensus in the limit. And now this is where I have to warn you that the energy argument we had before is now unfortunately out of the picture. So we do not have this beneficial situation where we can just look at almost sure things. Instead, you would have to rethink this limit in the consensus scenarios. What kind of limit are you talking about? And we don't have strong consensus, not only in the almost sure limit, we don't have any strong consensus, not even in probability. However, the model does have weak consensus in the mean. Now, since the opinions are bounded here, mean and probability is the same. Unfortunately, we couldn't succeed to work out if there is almost sure strong weak consensus or not. Like, I mean, if the weak consensus is almost sure sense or only in the L1 norm sense. So here I wrote down what that means in math, that the distance between two neighbors, the expectation of that is going to 0 as t goes to infinity. So here it actually is more than a technical, annoying intermediate scenario that you want to rule out. It actually takes place. And how does the proof of that go? Well, that you can rule out strong consensus is kind of cute. So that proof is a little bit more than a sketch, maybe. Because if you have strong consensus in almost sure sense, and realize this is less than I claim here, like if I can prove that. So I want to rule out it in the almost sure sense first. Well, if it was a strong consensus in almost sure sense, then everybody converges to some random limit, big L, let's say. And the distance to this opinion goes to 0 for everybody. So again, B is a translation invariant event. So it has to be by ergodicity either 0 or 1, like the probability of it. But we can also look at this L a bit closer, and just by the rotational symmetry of the model, we know that L will lie in -1, 0, just as much as it lies in between 0 and 1, because we can turn the circle and nothing changes. So if we intersect this set B with that L is negative or positive, whatever you like better, it will have probability 1/2 by symmetry, but also 0 or 1, because also this intersection is still a translation invariant set event. But as you understand, it cannot be both, either 0 or 1 and 1/2, so that doesn't work. And by that, we ruled out that the strong consensus is in almost sure sense. Now, how would you do if to rule out a strong consensus in a weaker sense, in probability? Well, what you do is you basically apply this subsequence argument. If I have a sequence of random variables that converge in probability, I can find a subsequence, or any subsequence, I can find a subsequence of that converges almost surely. So you would think about the time to be the index, let's say. Maybe we take all positive integers as the time indices we want to look at. And then you can choose a subsequence where they converge almost surely in the origin, and then you choose a subsequence of that where also at the point 1 they converge almost surely. And you keep doing that inductively, and you use Cantor's diagonal argument, and you would have a sequence of time points where all the vertices converge almost surely towards this limit. And then we're back to what cannot happen. So we can be sure there is no form of strong consensus going on. Now, the proof that there is a weak consensus in the mean, that's a bit more technical, so I don't want to walk you through that. But the crucial parts are that this you can show that this the expectations of the difference of two neighboring opinions is non-increasing in T. Observe the difference itself very well can jump up and down. I'm talking here about the expectation of the difference, and that one is non-increasing, that you can show with the classical jumping back and forth between stochastic averaging and spatial averaging with help of ergodicity arguments. And the spatial one is non-increasing, so the stochastic one has to be. And once you show that, since it's a positive sequence in T, or like a positive function in T, and it's non-increasing, it has to converge to something. And if this something was a delta bigger than 0, you could force it to, or you can show it that it would even decrease in the next bigger time interval by just the right people talking to each other. So if it was converging to something positive, it has to go down even more, and by that contradicting that it converges there. And by that you show it goes to 0. Now, let me already meet potential questions that you don't post but might have in your head. What happens if I introduce here a confidence bound? The part A is still the same, so that was only based on symmetries and yeah, basically symmetries of the model. Works exactly the same for any confidence bound you might come up with for this model. The second part, however, will not work like that. There you would have to think harder than we did, and I guess quite a bit harder to prove something there. However, if you say, okay, let's drop this confidence bound stuff and instead think of higher dimensions, even there the second part is still the annoying part. So B is still the annoying part, because there, unfortunately, a compromise between two people might actually increase the spatial distance, the spatial average of differences, because if two people come closer, but they have more than two other neighbors, it can actually raise the total sum of differences in that area. So by having many neighbors, if you have this very weird other neighbor that drags you closer to his strange opinion, you might create more difference to a lot of other neighbors, and that in total increases the difference. So that this is going down here, this expectation is not true for higher dimensions. And this is actually a very crucial part that sort of showed up as a hinder for me more than once, because also in the other results on the default model, you have the same problem that where we were dealing with those epsilon flat points. In principle, you could do the same thing in higher dimension. Well, you have to make sense of what kind of spatial smoothness you require. But the problem here is still that even this one might even hold also in higher dimensions, but there are too many neighbors, or like too many other agents at a given distance. On Z, you have exactly two of them. On ZD, it's already of the order of the distance. So this contribution from a given distance is constant. It's not going to 0. So that means even if you could come up with the same refined argument, it will completely break down here, because your opinion can be turned again upside down by just many other people from far away influencing people in your direction. So let me just recap on the open problems. So I hope I made you interested in those models and raised the number of clicks on the YouTube video. So maybe you even, once you watched it twice or 3 times, want to start working on this. So first of all, maybe let me give you the literature, the standard reference on interacting particle systems, also those in sociophysics like Voto model and stuff, you'll find in the book by Leggett. Then this bounded confidence model was first introduced by, as I said before, No, Amblar, and Weisbuch in 2000. I only quoted here or cited the proof for the phase transition of the simplest of those cases on said Hegström, but there's a paper by Lanchier where the same thing. But to be fair, Lanchier actually proved weak consensus, interestingly enough. So a phase transition from disagreement to weak consensus at the critical value of half, while Ulle proved strong consensus. And then most other things about the default model, you will find it in this fourth citation here, and the newest one about the compass model is the last one. So open problems, if you want to start, I would suggest ZD and the default model, because there it really seems that we're far off from any reasonable result to settle on. That you cannot show, for example, that there is disagreement for small confidence bounds is very, very peculiar. I think we're just missing some crucial ideas there that would help. When it comes to the compass model, for example, what is, or if you're even braver, try the critical case. That would earn my applause, definitely. I mean, already trying, but also the succeeding for sure. And with the compass model, for example, what is still a surprising fact is that we cannot rule out, or we cannot decide whether this weak consensus is almost sure or not. But that was all I wanted to say. I guess time is sort of up, or rather, the time left I wanna use for discussion. So I thank you for your staying with me all the way and your attention. And please feel free to shoot with your questions.
Thanks a lot, Timo, for this lovely talk. There is a question already in the chat.
I see it. There's a question. Is there no influence of the type of distribution and distributional characteristics on 0, 1? So now I don't really sort of understand the questions, I'm afraid. You mean what kind of distribution you have on 0, 1, right?
If I may just interrupt, basically you were saying this codes for general distributions, right? You have it on this slide.
We're talking about this, right?
Yes, in place of the uniform.
Yes. So what is interesting, I think now I understand the question. What is interesting about this distribution, this general distribution, are only those two. So in some sense, the form of the distribution definitely comes in by the mean. But let's say you take any distribution that is symmetric around the half and has no gaps, the answer will be a half, no matter is it concentrated near the mean or is it not. So what is actually crucial for the critical value is only the distance from the expectation to the far ends, and if there are gaps. So the exact form of it is irrelevant, at least for the critical case, maybe not for the speed of the convergence.
This explains. Thanks.
Michele has a question. Unmute yourself and ask it.
Yes, thanks. I was wondering if in this case, agents are cooperative. I mean, each agent imitates the other, no?
Yes. Mm-hmm.
But what happens if the agents are anti-cooperative? I mean, if the distance they interact, if the distance is larger than a fixed number, than theta.
Yes. So what you're saying, I think, yeah, I looked in this direction. So what you're saying is, isn't it reasonable that if a very much right-wing person meets a very much left-wing person, that they push each other even further in the spectrum? That leads to one technical problem. Either you say, okay, all opinions, all of R is a possible opinion, so you don't bound it, or you would have to force them, once they're at 0, at 1, you stop them. So you cannot get more extreme than that. Both have disadvantages. If you allow them to walk off as much as they want, that's what the limit will be. Like there will be a pair of neighbors that push each other to extremes, and that will just lead to disagreement no matter what. If, however, you stop them, then you would have the problem that you lose this average preserving behavior. So how would you do that if I'm sitting at a 0 and you're sitting at 0.9? So I push you away, but you cannot push me away. So the average would change. You can help that by saying, okay, if I cannot move, then you don't move either. But then we're questioning presumably how much more realistic that becomes. So you can do simulations, and basically the result is pretty non-interesting. So if you allow them to push each other, it's basically a big fragment, a big mess going on.
Okay. If they don't move at all, I mean, okay, maybe from 0.8 you meet someone that is 0.8 and don't move.
How do you mean? If you move a person having exact your opinion, you will definitely leave with the same opinion. There is no, because the step you take towards the average is
okay.
a zero step.
See, I understand. Sorry.
So what is criticized in this model sometimes is that you basically the cutoff is very sharp. So until a certain tolerance, the influence is like most, and then just a mu or an epsilon later, you don't listen to this person whatsoever. That's definitely something that has to be criticized. On the other hand, this effect that people that you still have in your tolerance horizon, let's say, but have a very alien opinion to you, change your opinion most, that is not so unrealistic. I mean, if you people that think the same, your opinion won't change much, right? So that's.
And I have another question, if I can. If maybe a curiosity, if theta is changing in time, I mean, theta is the parameter in which they interact, two agents. It's fixed at the beginning, but can be changing, I mean, with some distribution or something like this.
So there has been work done both if theta is not uniform, that means different agents have different tolerances. What happens there, I mean, those are based on simulations, it's not rigorous results, but what happens there is basically that the largest tolerance decides. So what would happen is that the people that are most tolerant decide whether there is a disagreement or consensus. But your question was more if you let theta depend on time, so that people maybe get older and get less tolerant with time. That's not so unrealistic either. Yes, there is actually a very nice paper in the area of clustering algorithms, where you sort of try to find out a good way of divide your graph in cliques. I mean, there are many algorithms for that, minimum cut and stuff. And one of them is, okay, I run this default model, and theta t just goes down in time. So that means people that are strongly connected have the chance to average out, while people that are weakly connected, or groups that are weakly connected, they will get hit by the tolerance going to 0, and then will stop talking to each other because their opinions are too far apart. That was really unexpected and interesting work in this direction. However, for the rigorous results here, I looked at it for trying to tackle the critical case. So you think about theta t approaching a half from one side. What happens is, if it approaches from supercritical side, it's behaving supercritically. If it's approaching from the subcritical side, it's behaving subcritically. If it's jumping back and forth, you cannot say a thing, or I cannot say a thing. So not really something I want to add to my slides in that respect.
Thank you very much.
Well, there's another question in the chat by Raphael.
I saw that. The question was, are there any rigorous results on finite graphs? Well, rigorous and rigorous. I mean, this phase transition from one behavior to the other, you cannot have, because on a finite graph, it will be always depending on the initial configuration, right? You can come up with a very weird initial configuration where everybody's stuck from the beginning, no matter how big the theta is. On the other hand, no matter how the graph looks like or the theta looks like, you can find a very nice, smooth configuration where there will be consensus. So there is, as far as I know, there is no quantitative results on finite graphs, how the probability behaves depending on the network and the finite network and the parameter theta. In fact, there it might even depend on the mu.
Okay, if there are no further questions, I suggest that we unmute ourselves and give Timo an applause. So, personal remark is what I like always about opinion dynamics is that the sessions always tend to be quite interactive. I think it's a topic where a lot of people have an opinion about. So this was a very nice session, and I thank all of you for your contributions. And if there are no further comments, I suggest that you, Timo, stop sharing, and I will stop the recording, but leave open the session.